Deep in the heart of the western Utah desert, a group of scientists from the University of Utah are studying the highest energy particles known to man, found in cosmic rays. The term cosmic rays refers to elementary particles, nuclei, and electromagnetic radiation of extraterrestrial origin. They were first discovered by Austrian scientist Victor Hess. In 1912, Hess was studying background radiation. Hess ascended in a balloon and took measurements at different altitudes. He found that background levels increased as he went higher. From these measurements, Hess concluded that the radiation he was studying was coming from outer space. He called it cosmic radiation, which later evolved into cosmic rays. In 1936, Hess was awarded the Nobel Prize for this discovery. The cosmic rays that are being studied by the University of Utah scientists have much higher energies than those originally measured by Hess. These particles have energies over 10 to the 18th electron volts and are referred to by scientists as ultra-high energy cosmic rays.
An electron volt is a unit of energy. In fact, it's the amount of energy that an electron will have if it's been accelerated through 1 volt of potential difference. We illustrate this with a common example of an ordinary D-cell battery. D-cell battery is rated at 1.5 volts. That means that an electron in this battery is going to get accelerated to 1.5 electron volts. In our example, the battery is hooked up to a light bulb. So this electron would carry that energy to the light bulb, and in the light bulb it would transfer that energy over to heat and light. Common chemical processes like the one we just looked at are on the scale of about 1 electron volt. Nuclear processes are in the order of a mega electron volt, or 1 million electron volts. The rest mass energy of a proton is about a giga electron volt. And the current accelerators that are in operation, which are at the limit of our technology, are up to a tera electron volt. We, however, are looking at particles with 10 to the 18th electron volts. So we would have to add another 6 zeros onto this number to illustrate the energies at which we're looking.
The mystery of ultra-high energy cosmic rays lies in 3 basic questions. What are they?
Cosmic ray is a particle, subatomic particle, like atoms are composed of, that comes from space. There are some processes in the universe that produce them at very, very high energies.
Scientists think they are mostly protons. At somewhat lower energies, cosmic rays are 50% protons, 25% alpha particles, 13% CNO nuclei, less than 1% electrons, and less than 0.1% are gamma rays. How are these particles being accelerated?
Really, there's no known mechanism to generate the energies that these particles have. Active galactic nuclei. What you need is a very strong accelerating field over a very large distance.
There are some plausible theories based on ideas of Enrico Fermi.
He speculated that it is possible for charged particles to bounce off of magnetic clouds, plasma clouds, which permeate the universe. And by a sort of statistical process of collisions, some of these particles can gain very high energies. More recently, people have looked at modifications to this theory whereby you can have particles bouncing around at the front of shock waves, such as you might find in a supernova explosion. There are significant problems to all of these theories, mostly because you need an enormous object, and you need to be able to confine these particles within the accelerating region.
This question ties in closely with the third question. Where do they come from? Suspected sources are large, energetic structures where strong shock are found. For example, supernovas. There are problems with this idea because supernovae are not large enough to explain energies greater than 10 to the 18th electron volts. The existence of ultra-high energy cosmic rays suggests that somewhere in the universe there may be extremely powerful forces which we do not yet understand.
Yeah, we're going after very difficult questions, trying to see what's out there and what's, what is the nature of the universe. We're trying to answer, why are we here? What is the universe? What is the world we're in? Very fundamental questions.
Ultra-high energy cosmic rays are rare.
At energies less than 10 to the 14th electron volts, the flux of cosmic rays is large enough for direct detection. An instrument can be sent up to greater than 100,000 feet outside the atmosphere, aboard a balloon or on a satellite. A detector that is 1 meter by 1 meter can typically detect millions or even billions of events per year. The cosmic ray flux, or the number of particles per unit area per second, drops very quickly with increasing energy. At greater than 10 to the 18th electron volts, the same 1 meter square detector would see less than one event every 50 years. Direct measurement of ultra-high energy cosmic rays is therefore impractical.
The solution to this problem is to use the Earth's atmosphere itself as part of the detector. When a cosmic ray enters the upper atmosphere, it collides with the nucleus. This collision produces an avalanche of secondary particles, which in turn leads to further collisions. This process leads to a cascade of particles called an extensive air shower, which can grow in number to 1 billion or more. An air shower leaves a faint glow of fluorescent light in its trail, resembling a 100-watt ultraviolet light bulb moving at the speed of light. This flash of light lasts only a few millionths of a second and cannot be seen with the naked eye. It can, however, be seen by fast, sensitive electronic cameras on clear, moonless nights. This method of detection is known as the fluorescence technique, originally proposed by Cornell University scientist Kenneth Greisen. The initial attempts in the late 60s at Cornell were not entirely successful because the detector was not sufficiently large and the atmospheric transmission was poor in upstate New York. In 1976, a group of University of Utah scientists brought new prototype detectors to Volcano Ranch, New Mexico. The clean atmosphere of the desert was well suited to this type of measurement. Their efforts produced the first successful detection of air showers using the fluorescence technique. The success led to a new experiment in the western Utah desert, which became known as the Fly's Eye. The Fly's Eye was built over the Ochre Mountains west of Salt Lake City on the Dugway Army Proving Grounds. This experiment collected light from air showers using 1.5 meter spherical mirrors. The light is focused onto an array of photomultiplier tubes, which transform the light pulse into electronic signals. The experiment operated 101 mirrors at 2 sites, separated by 3.4 kilometers. Each mirror was instrumented with 12 or 14 pixels, each covering a 5-degree cone in the sky. The pixels cover the sky in a manner reminiscent of the compound eye of a fly, hence the name Fly's Eye. The Fly's Eye was in operation for 12 years from 1981 to 1993. In 1991, an important discovery was made at Fly's Eye. A single particle with an energy of 3.2 times 10 to the 20th electron volt was detected on November 15th. This single particle had an energy comparable to that of a Nolan Ryan fastball. It was and still is the highest energy ever measured in a single particle. This detection has severe implications to astrophysics. At energies above 6 times 10 to the 19th electron volt, it becomes possible for cosmic protons to interact with photons in the microwave background radiation. The theoretical cutoff of the cosmic ray spectrum was first suggested by Greisen, Zatsepin, and Kuzmin, shortly after the discovery of the microwave background in 1965.
This is a photomultiplier tube. It's sort of the basic element of our detector. So we plug 256 of these into one camera, and then these are the pixels of the camera. And the light comes in, gets collected and focused by a mirror, and gets focused onto the front surface of this detector. So it takes light in and gives you an electrical signal out, which you can then process with further electronics and read it out by your computer and figure out what's going on.
The improved resolution of the detector allows the experiment to resolve air showers up to 25 miles away compared to about 8 miles for the original fly's eye. This extended reach gives HiRes an effective collection area roughly 10 times that of the fly's eye, so that HiRes can collect as many cosmic ray showers in 1 year, that which took fly's eye a full 10 years of operation. The HiRes experiment was designed for stereo observation with 2 detector sites separated by about 8 miles. To minimize observation by ground fog and aerosol contamination, the detectors sit on hilltops about 500 feet above the desert floor. The first site, located at Little Granite Mountain, was completed in 1997 and houses 22 mirrors. These mirrors cover elevation angles up to 15 degrees in all directions. Because HiRes looks out as far as 25 miles and the atmosphere is only about 5 miles thick, it is not necessary to provide full sky coverage like the fly's eye did. The first site takes still photographs of the air showers with an exposure time of 6 millionths of a second. A second, more advanced site was completed in 1999, hosting 42 mirrors, which covered the sky up to 30 degrees in elevation. These mirrors are located at Camel's Back Ridge and take motion pictures of the air showers at the rate of 10 millionth frames per second.
So for instance, if the shower is very far away and stays inside of a single photo tube for, say, a microsecond or so, we will have 10 photographs of that part of the shower as it goes across that single photo tube. So that gives us even more resolution, and we can see the shower develop in a much more detailed manner.
As of summer 2000, HiRes has already accumulated 3 years of monocular and 1 year of stereo data. This already represents the longest cosmic ray data set ever collected. HiRes will operate for at least another 5 years.
What drew me to cosmic rays is really the fact that it's a completely open and unknown field, unknown entity out there in physics.
What interests me most in this field, as a particle physicist, which my training is, you are trained, you grew up in an environment of this really antiseptic accelerator facility. And here you have an experiment where you get to do very fundamental physics in a completely different setting. Imagine yourself out at one of our sites. You arrive there at around sunset, and it's usually a gorgeous sunset. And the sun goes down before the moon comes up on the nights we run. You turn on your detector, and you have this complete quiet darkness out there.
In the near future, HiRes physicists in the U.S. are working with Japanese colleagues to develop an 11-site experiment stretching from Dugway to Millard County, Utah.
To really be able to study the phenomena in a more detailed manner, we would need more statistics, and to do so we need a larger detector. So presently there are plans to expand south of the Dugway Proving Grounds and construct up to 11 sites in total, which would cover about 100,000 square kilometers.
The new telescope array experiment will extend the collection area another factor of 10. Also on the drawing board at NASA is the orbiting wide-angle lens, or the OWL, which will place fluorescence detectors in high Earth orbit looking down at air showers in the atmosphere. A prototype, the Extreme Universe Space Observatory, or USO, will be deployed by the European Space Agency aboard the International Space Station toward the end of the decade.
We look out with normal visible telescopes and radio telescopes. We look, where did this extremely high energy charged particle come from? Well, there's nothing out there that looks mysterious, nothing out there that we would believe would be generating such high energy particles, nothing so violent out there, so what's going on? It's a big mystery.
Solving the mystery of these ultra-high energy cosmic rays may lead to a new model of the origin and formation of the universe.